This is a multidisciplinary work that involves different types of institutions. There are our collaborators. Firstly, the National Laboratory of Scientific Computing. The second one is the Federal Center of Technological Education, Celso da Fonseca, both of them in Rio de Janeiro, Brazil, and the National High Technology Center in Costa Rica. Our points that are going to be presented in here, it's the bioinformatics project, that the goal is transition bioinformatics scientific gateways to HPC. The other is the scientific gateway BioInfo portal. I'm going to present the architecture functionality and the proposed AP for ML, that is the BioInfo portal 50 level, the 3 bioinformatics experiments that were performed in the SUPERCOMPUTER Santos Dumont, an ongoing step for data analytics and machine learning. Well, this is the BioInfo portal project. This science gateway was developed by the Brazilian National High Performance Computing System, that is SINAPAT, which manage different types of clusters, for example, including the Santos Dumont supercomputer, that is considered the largest supercomputer in Latin America. As our BioInfo portal gateway, there are other portals that are also hosted in SINAPAT. The roadmap that I'm going to follow is presenting the BioInfo portal architecture for the functionality and the Santos Dumont integrations, the performance applications, and the machine learning components. The first is this architecture. This is a 4-level BioInfo portal gateway. The first one layer is the user interface that communicate the user with the architecture of the BioInfo portal gateway. The second one is the management layer that is represented with the CC Grid middleware that do the management between all the resources in the BioInfo portal gateway. The third is the data layer that is composed by different types of databases that store different types of information about the experiment, about the genomics data, or about the bioinformatic applications. And the other is the resource layer that is composed by different types of clusters, including the Santos Dumont clusters, where they are deployed all the application, the bioinformatic application, and also the libraries that are used. In this case, also are deployed the scientific workflow management systems. And the proposed MLAP is the 5th level that is going to be coupled to the BioInfo portal gateways. It is expected to be capable of adaptively distributing the workload, assuring fair response times, managing load balance, and ultimately providing an overall system improvement. ML is based on computational efficiency data gathered from previous experiments, which could be generalized by a learning model, enabling a smarter allocation of resources for the next experiments, aiming at the maximization of system usage and throughput. I am going to present 3 experiments that are bioinformatics experiments. The first one is the RAXML that use the Santos Dumont CPU resources. The experiment use different types of genomes. We explore different parameters of RAXML and different resources of the Santos Dumont. In the figure 2, we obtained the speed up and the computational time of all the execution of RAXML in Santos Dumont, and all this information is stored in our databases. In the following experiment, we use other bioinformatic application that is named BEAST for exploring the GPU and the CPU and the hybrid resources of Santos Dumont. We present this experiment that is a bioinformatic experiment, and also we explore the data, the parameter of the BEAST, and also the different types of architectures of Santos Dumont. We performed the different types of executions based on the total computational time and the speed up and other measurements. And then we stored all this information in our databases. And finally, the third experiment is based on the performance of the scientific workflows in Santos Dumont. The scientific workflows in Santos Dumont are used for concatenate different bioinformatic applications. Then we use Parcel, that is a parallel language for management these scientific workflows. Different type of experiments were performed, and then we explored the parameters of the different bioinformatic applications with the Parcel, and we stored all this information in our databases. Then, with this type of information, we are presenting the ongoing step based on data analytics and machine learning. As we can see, we construct the decision tree. This decision tree shows the input data or the input variables regarding the environment configurations. The target variable aims to represent overall execution quality. Preliminary results evidence that an ML approachable dependency between experiment parameters and computational efficiency, whose predictable enables its exploitations. We explore the construction of decision trees, but other type of model are capable to learn a more complex relationship based on neural networks or random forests or support vector machines. We can predict based on the execution time, based on the features of the genomics data or other type of features, which one is the environmental characteristic of features of the nodes of Santos Dumont that can be used for explore or for better explore or for obtain the better efficiency for each one of the experiments that can be performed in Santos Dumont. Then we are going to use this type of information for develop our 5-level AP that is based on machine learning for our BIOINFO portal. This BIOINFO portal, Science Gateway, was published in the 2020 as in FGCS, a scientific gateway for integrated bioinformatic application on the Brazilian National High Performance Computer Network. And these works are also related in the associated project of RISC-2, a network for supporting the coordination of high-performance computing research between Europe and Latin America.